Welcome to Module 13, Pressure Control for Laboratories and Critical Spaces. Pressure control protects airflow direction. It must be designed around leakage, doors, supply airflow, exhaust airflow, sensor installation, alarms, fallback, and recovery. In this module, we will separate pressure set point from the real objective, maintaining the approved directional airflow relationship under normal use, door operation, and failure conditions. The learning objectives are focused on field verification. Learners should explain positive, negative, and cascaded pressure relationships. They should distinguish direct pressure control from airflow offset control. They should coordinate supply, exhaust, doors, and modes. They should define stability, alarm delay, and recovery expectations. They should identify sensor installation risks and design failure response appropriate to the consequence of the space. The core concept is important. A pressure set point is not the ultimate objective. The objective is a directional airflow relationship under expected door and leakage conditions. The BAS may display a pressure number, but the professional has to understand what that number is protecting. In a laboratory isolation room, clean space, or hazardous room, pressure control must respect leakage, doors, ventilation, process needs, and equipment limits. Critical spaces may be positive, negative, or part of a pressure cascade. A positive space tends to push air outward toward the reference. A negative space tends to pull air inward from the reference. A cascade may use a corridor, anteroom, and critical room to create an ordered pressure path. The approved design should define the reference space, pressure direction, range, supply and exhaust requirements, door relationships, normal and emergency modes, alarm limits, and documentation requirements. There are two common approaches. Direct pressure control measures differential pressure and modulates supply or exhaust. It directly observes pressure, but it can become unstable when doors open, sensors are noisy, or actuators are too aggressive. Airflow offset control maintains a defined difference between supply and exhaust. It can be stable when airflow stations are reliable, but it does not directly measure the pressure outcome. Many critical spaces combine airflow tracking with pressure monitoring and slow trim. Door effects are one of the main reasons critical space pressure loops become unstable. Opening a door can collapse pressure quickly. The controller cannot always maintain differential pressure against a large open doorway without excessive airflow. If the loop reacts aggressively, it may drive exhaust to a limit and then overshoot when the door closes. Door-aware logic may hold integral, limit response, suppress short nuisance alarms, resume smoothly after closure, and alarm a door that remains open too long. Critical space pressure may be measured at very low differential values, so installation details matter. Review high and low tubing orientation, reference location, drafts, local velocity effects, tubing length, leaks, blocked ports, zero calibration, sensor range, mounting orientation, and penetration location. A sensor with a wide range may not have enough resolution for a low pressure set point. Before tuning the loop, verify the measurement chain. A pressure cascade is a coordinated path, not a set of independent loops. The design may identify the critical room as the primary controlled space, an anteroom as an intermediate reference, and a corridor as the building reference. The sequence should define supply and exhaust limits for each space and coordinated response during door operation. Commissioning should test doors individually and in realistic combinations. Pressure alarms should be actionable and context-aware. Consider high and low limits, door open delay, occupied or a process state, persistence, sensor validity, maintenance mode, and escalation based on consequence. An alarm should not be continuously active during normal door passage, but it also should not be delayed so long that a true loss of pressure goes unnoticed. Alarm timing must match the room use and risk. The worked example is a negative laboratory. The design target is -8 pascals relative to the corridor. Exhaust normally exceeds supply, minimum ventilation and exhaust requirements remain active, and short door openings are expected. A practical strategy uses local airflow loops for supply and exhaust. Exhaust set point equals supply plus the approved offset. The pressure loop slowly trims the offset within limits. When the door is open, the pressure loop integral is held. After the door closes, the loop resumes with bumpless transfer. If the pressure sensor fails, the system uses a conservative airflow fallback and alarms. Failure and fallback must match the consequence of the space. A failed pressure sensor may require airflow offset fallback and an alarm. A door held open may require escalation after an approved delay. Supply or exhaust airflow failure may require immediate operator response or define safe mode. Network loss should not remove local protections when local control is practical. Maintenance mode must be visible, time-limited, and authorized. Fallback should not become permanent operation. Before changing pressure set points or tuning, use a diagnostic evidence path. Confirm the approved design intent, verify the reference space, validate the pressure sensor and tubing, check door status, trend supply airflow, exhaust airflow, pressure, control outputs, mode, alarms, and sensor validity. Review airflow limits and failure response, then test recovery. Critical space pressure settings should not be changed casually. They often require multidisciplinary approval. Best practice starts with clear ownership and testable logic. Document pressure direction, range, reference, and modes. Use airflow limits to constrain pressure loop behavior. Hold or limit integral during door open conditions. Verify sensor range, tubing, zero, and reference location. Commission cascade spaces together. Make maintenance and fallback modes visible and time-limited. Write alarms that include door state and sensor validity. Require approved review before changing set points or alarm delays. Let us summarize. Pressure control protects airflow direction under real room use. A pressure set point supports a directional airflow objective. Direct pressure control and airflow offset control prove different things. Door operation can create impossible control conditions that require door-aware logic. Sensor installation and reference location can dominate performance. Finally, alarms, fallback, and recovery must match the consequence of the room. In the next module, we will move to rooftop units, heat pumps, and unitary equipment.